Hello and welcome to today's video. So far, we've seen how an inverse matrix is defined. We've seen that there are actually matrices that have an inverse, and there are matrices that don't have an inverse. We've seen some rules for working with inverse matrices, and we've also found a criterion that says a matrix can be inverted if and only if it has rank n. Now, of course, what we'd like to see is a method that gives us an inverse matrix if it exists, and maybe a proof that no inverse matrix can be found if it doesn't exist. And actually, we've almost been there. So in this section, we are going to work out the details of that method. And that is called computing an inverse matrix. So let me give you a quick recap of what we did already in one of the last videos. Let's say we have a matrix A in R to the n by n. Now, if we want to find an inverse matrix, then what can we do? We need to assume that the matrix has full rank. Otherwise, we know it cannot be inverted. So let's assume it has rank n. We want to find a matrix B with A times B equals the identity. And what that means is, for each column of B, we have a system of linear equations. So let's call those columns B1, B2, and so on, up to Bn of B. A system of linear equations of the following form holds. And form is, well, what we have is, of course, this product A times B. That can also be seen as multiplying the matrix A first with the first column of B, then with the second column of B, then with the third column of B, and so on. And each of those gives one column of the resulting matrix here. So if you multiply A with the first column of B, that's the first column of the result. And the first column of the result, this matrix here, the identity, is the first unit vector. A times B2 is the second column of the result. And the second column of the result is the second unit vector, U2. And so on. So that works up to ABN equals UN. So what that means is, if we want to determine this matrix B, we can just compute solutions to all of these equations here. So to determine B1, B2, and so on, we need to find solutions to the systems of linear equations AX equals U1, AX equals U2, and so on, up to AX equals UN. So what we have here is n different systems of linear equations, each with the same left-hand side, that coefficient matrix A, and with a different right-hand side. N systems of linear equations with the same coefficient matrix and different right-hand sides. And those right-hand sides are U1 to UN. Now, if you solve a system of linear equations through Gaussian elimination, the steps required to do this are determined only by the left-hand side, by the coefficient matrix. So those necessary steps are going to be the same for every right-hand side. And that means what we can do is we can just determine a solution with that same left-hand side and with all right-hand sides simultaneously. So what we can do is we can perform Gaussian elimination with all right-hand sides simultaneously. And if we carry that as far as the reduced echelon form, which we normally don't do, but if we do that in this context here, then it's very easy to read off the solution in the end. So that's why we're going to do this now. It's worth the trouble because we're solving n systems at the same time. So we will use reduced Rao echelon form to be able to see the solutions easily. And well, reduced Rao echelon form, what does that mean? Well, for a matrix, an n by n matrix that has rank n, that means each column will have a pivot element. And reduced Rao echelon form means the pivots are all ones. There's zeros below the pivots, and there's zeros above the pivots. So we have ones on the diagonal, and we have zeros everywhere else. So what we get for our left-hand side in reduced echelon form is actually an identity matrix. So for a matrix A of rank n, the reduced Rao echelon form will be the identity matrix IN. And then on the right-hand side, we have those right-hand sides there. And that means we can read off the solutions immediately. So the right-hand side, those will then be the vectors B, B1, B2, B3, and so on that we actually want. So the right-hand sides in the final tableau will be the desired vectors B1, B2, and so on to Bn. So let's summarize that procedure. Again, we'll start with an n by n matrix. And what I claim is the following procedure will either determine an inverse of A, or it will give a proof that there is no such inverse because A doesn't have rank n. So the following procedure determines whether A is invertible, and if so, computes an inverse. And the procedure works in the following way. We start with a tableau of the form A on the left-hand side, unit vectors on the right-hand side, so that's just an IN, an identity matrix on the right-hand side. So this says n simultaneous right-hand sides. Then what we do is we perform row operations, we perform Gaussian elimination to obtain a tableau, let's say first in echelon form. So we perform row operations to obtain a tableau in echelon form. Now what this tableau gives us is the rank of A. We can now have a look at the pivots, and if we find n pivots, then the rank of A is n. If we do not find n pivots, then A doesn't have full rank, and that means we can stop right here. There will not be an inverse. So if rank A turns out to be less than n, then A is non-invertible, and that means we can stop. Otherwise, we go to step 3. And step 3 performs further row operations to obtain reduced echelon form. So that will be of the form, the final tableau is of the form some IN on the left, we argued, reduced row echelon form of a full rank quadratic matrix that will be an identity matrix. And then the right-hand side is some other matrix B. And this resulting matrix is then the inverse of A. Then B is the inverse of A. So A to the minus 1 equals B. And this is the procedure for computing an inverse matrix. So in particular, you don't have to care about whether this matrix is invertible or not. You can just start the procedure. It's only halfway through that you have to have a look at the rank of the resulting matrix. And if it turns out that the rank is too low, you can stop right there. So basically, if there is no way that you can obtain the identity matrix on the left-hand side, whenever you find that out, that's when you stop. Otherwise, you go on until you have that identity matrix on the left, and then the right-hand side will give you the inverse matrix to the one that you started with. So that's the procedure that we're going to use mostly. And I'll see you in one of the next videos where I'll give you a few examples of how to apply that procedure to compute actual inverse matrices.